Okay, so now I want to clarify a little bit about how you calculate variance. You have the activity that you're working on this, and so I can see why this would be really, really salient and a real concern right now. And it's also important because no matter what kind of behavior science you're doing, you're going to have to know how to calculate variability. Okay, and variance is one of the most is one of the simpler approaches to doing it. Okay, so when we're looking at our equation for variance, it's the sum of the mean minus some number squared. Okay, so the sum of all those differences, squared differences divided by the number. Okay, of observations that you have here. To illustrate this, I'm going to go through kind of a step-by-step simple approach to calculating variance with two sets of numbers that have different variances, even though they have the same mean. Okay, so the mean of each of these is 5. Okay, demonstrate. I put these together so that they would absolutely have a mean of 5. Okay, and so mean minus the number. So we have 5 minus the number being 3 equals 2. 2 squared equals 4. Okay? 5 minus 4 equals 1. 1 squared equals 1. Okay? 5 minus 5 equals 0. 0 squared equals 0. 5 minus 6 equals negative 1. So this right here demonstrates why it is that we have to square the values, okay? Because negative 1, if you square that, that becomes 1. So negative 1 times negative 1 is 1. However, 5 minus 7 equals negative 2, okay? Equals negative 2 times negative 2 equals 4, okay? But look what happens if I were to add up all of these numbers. So 2 plus 1 plus 0, that's 3. Plus a negative 1, that's 2. A negative 2. Now you're down to 0. So it would say that you have no variability. And we know that that's not the case, okay? So we know that your variability there is for 5 divided by the number 5 equals 1. Okay? So it's relatively straightforward approach to calculating variability. Here is a whole different set of numbers. Okay? And so we have 5 minus 1 equals 4 squared equals 16. Okay? 5 minus 3 equals 2 squared equals 4. 5 minus 5 equals 0. Square 0, it still equals 0. 5 minus 7 equals negative 2 equals, you square negative 2, and you get 4. 5 minus 9 equals negative 4. Negative 4 squared is 16. So you add those up, and you have 20, 40. 40 divided by 5 equals 8. Okay, and this set of numbers were obviously had more variability in the first place. I increased or decreased by 2 this time as opposed to increasing or decreasing by 1. Okay, so that is how you end up getting markedly different variances. Okay, I will note there's a lot of ways in which you can get lost. This was a very step by step, so I took the m minus the number. Okay. Then I went and I squared it. And I got those numbers. And then once I got all those individual numbers, I summed them up and then divided them by n. Okay? This is a relatively simple approach. Okay? If you do it this way, you will not make errors. And not making errors is kind of what you're hoping to do. So, another question that came up, okay, is a question surrounding the issue of one versus two-tailed tests. Okay, so here we're looking at distributions. Okay, so normal distribution, and I'll even draw two of these. Normal distribution. Okay, now we have our distributions. If we do a one-tailed test, we're going to look for we're looking for, there's 5% out on the tails of these distributions, okay? So with the one-tailed test, you're going to say all 5% are over here. 5%, okay? However, if you're going to do a two-tailed test, you're going to go further out to the edges because now this is just 2.5%, okay? 2.5%. Okay, so the idea is you'll see more type 1 errors because there's more values that are going to fall in here just by chance than are going to fall in these little 2.5 spots there. So you have higher levels of type 1 error with a two-tailed test. Why would one use the one-tailed test? Okay, sometimes people have hypotheses that are directional, okay? So, for example, my daughters are very competitive with one another. My younger one might say, I'm faster than you, okay? And so she's hypothesizing that if they were to run a race, her time would be lower than her sister's, okay? By contrast, the two-tailed test is saying, hey, we're not the same, okay? Didn't matter if she's faster or slower, just, hey, we're not the same, okay? That's a foundational difference, okay? Lastly, okay, I want to try to get through. I'm trying on this. Please let me keep trying until we get it right, okay? Type 1 versus type 2 error. Okay, let's start off with the most simple statement of this. A type 1 error is saying that there's an effect when there is no effect, okay? And it does, it doesn't mean that you're being dishonest about what your data say. Your data could actually indicate that there's an effect. You could have made something in your experiment may have yielded data that were some sort of an error, okay? So it's not malicious or anything of the sort, okay? Type 2 error is saying that there is no effect when there is one. And again, this isn't, explicitly trying to hide an effect or anything like that. Sometimes you may have sampled the wrong things to suggest that there was an error, okay? It gets complicated when it comes to adding the null hypothesis piece to that. And unfortunately, the type 1 and type 2 errors are oriented around the null hypothesis. The null hypothesis is saying that there is no effect, okay? So if you say that there is no effect, your null hypothesis, and there is actually no effect in nature, yay. You are not, you fail to reject that null hypothesis. There's no error to that, okay? You say, you have your null hypothesis saying that there is no effect, and you actually find an effect. Okay, yay! It turns out there actually was also an effect in nature. That's another correct thing. So with my two children being competitive about how fast they run, if one girl said, "Hey, I'm faster than you," the other one says, "No, you're not faster than me." There's no difference in how fast we run. The other one, she gave the null hypothesis. There is no difference, okay? And if we start running a race and based on the measurements that I take, it turns out that the little one runs faster, okay? Based on the measurements that I take. However, what actually did happen was I made a mistake when I was using my stopwatch, okay? So she actually didn't run any faster. I just didn't start the stopwatch as quickly as I should have. So there was no difference in nature. If I were to put them in a foot race side by side, they would end up in the same spot, okay? However, based on an error that I made in terms of operating my stopwatch, I made it look like there was a difference. that would be a type 1 error. It'd be particularly important because I'd tell the little one that she's faster than the big one, and she'd get a big old head and all this sort of thing. Okay, big problem. Okay. By contrast, if based on them running and the errors that I make messing around with the stopwatch, because none of us are perfect, I actually say that there's no difference between the two of them. But if I were to put them in a side-by-side foot race, the little one is much quicker. Okay, I would have said there's no effect. So I would have accepted the null hypothesis that there is no difference between the two of them, but I would have been wrong. Okay, and in that case, that would be a type 2 error. Okay, so type 1, saying there is an effect when there isn't one. Type 2, saying there is no effect when there actually is one. Okay, I hope everybody is doing well. Again, we are available for you via email. We'll set up Zoom meetings. Hopefully everybody's making through this whole thing okay. And I wish everybody a great remainder of the semester. See you next week.